Okay, so this is week 3 in CENG501 deep learning, and today we are going to look at several different topics, but mainly multi-layer perceptrons. Last week, as you remember, we have looked at concepts in machine learning. We have gone over these concepts through supervised learning example. We have seen maximum likelihood, maximum a posteriori estimation, briefly talked about biological neuron, and briefly introduced the artificial neuron. These were the last week topics. And today we have one piece of leftover from last week. We are going to derive the cross-entropy loss using as a maximum likelihood estimation. And then we will look at artificial neuron, perceptron, learning rule, MLPs, activation functions, initialization, backpropagation, SGD, momentum, and so on. It looks like a lot of topics, but each of them are short, so we will probably fit all of these to today's lecture. This week's recommended reading are 2 sections from chapter 8 of the deep learning book. These are about optimization, numerical optimization and gradient descent. These are things that we assume that you know, so this is just recommended. It's a good text. It's recommended that you read it to refresh your optimization and gradient descent knowledge. So a recap of supervised learning. We called X as input, Y as the ground truth label, which is coming from the data set. Usually humans annotate this, humans provide this. We called the function F the model, and F processes the input X and then produces a prediction Y hat. And then we compare the prediction Y hat with the ground truth Y, and we called it a loss. And the overall cost or objective function that we minimize to learn the parameters of a neural network looks like this. And we have typically 2 types of terms. One of them minimizes the error on the training examples. This is called empirical risk in statistical learning. So this loss reduces the training error. Another loss type regularizes the model. So this R theta regularizes the model. There are different types of regularizers, as we are going to see in the upcoming lectures. So cross entropy, we already introduced it. We already derived it from Kullback library divergence. What we do here is Y is the ground truth label coming from the data set, and Yi is the label for the ith example. And it's a C-dimensional one-hot vector. C here being capital C is the number of classes. Okay? And here we denote YIC, an individual element of the label vector. We multiply that with log of the predicted probability for that specific example and for that class by the model. To obtain probabilities from the model, we use the softmax normalization, which is exponential of the logit divided by sum of exponentials of the logits. So this already you know. And I'd like to now show you how this thing is, where does it come from, okay? So remember the maximum likelihood estimation where we assumed a probability model parameterized by theta, and we tried to maximize the likelihood of data under this probability model. And to deal with that, since you can it's very difficult to define a probabilistic model over an entire data set. What we do is make the IID assumption and make this joint probability, factorize it into this product, where individual data examples, likelihood of individual data examples are multiplied together. We take the log to work with the sum, which is easier, and then the rest will be, the rest of the derivation will depend on the specific form of P model, whatever you use for it. And we are going to look at cross entropy here. So we want to maximize over model parameters this probability. These are capital XY under this. So we want to maximize the likelihood of labels given the data. You know, I sometimes use the probability, sometimes use likelihood, but as the data set is already an observed thing, X and Y is given to us from the data set, it is observed. So that's why we talk about its likelihood. So P of Y is the likelihood of the labels. We factorize this into examples. So that, let's say we have n examples. Now we have xi. So probability of the label yi given data example xi under this parametric model parameterized by theta. Here yi is a one hot vector, c dimensional. Okay. To work with this, okay, before that, let's expand yi. So max theta. Because yi consists of zeros and ones, I can further expand this term into this product. Do you agree with me? So yi, let's say class 1, xi, probability of yi 2, xi theta, and so on. So probability of y I c xi theta. So you can further this becomes another product yi c xi theta, right? Okay, I forgot one thing here. Okay, so in the exponent of each of these expressions, I can write IC, because each of them is either 0 or 1, right? If it's 0, something to the exponent 0 is 1. If it's 1, only that term is effective. So this is YIC. Any questions? So far, so good. Yes.
Question about the notation.
Yes.
Dash and the semicolon specifically.
You mean the theta before the semicolon theta?
Yes.
So, okay, the vertical column means given, so probability of yi given xi. theta is the parameters of the probabilistic model. So theta is the parameters. Okay. So if I take the log, take log of this, what will happen? So this is equivalent optimization problem. So we are going to have a summation over data points, a summation over classes. The exponent becomes a factor. So yic log of p yic xi parameterized by theta. So this is cross entropy loss function itself, except this is maximization. If you put a minus and turn it into a minimization, then this is cross entropy. Of course, this part is the predicted probability of the model for the ith example seed class. So this thing is, we usually represented this with QIC, and we obtain this using softmax, right? Let's say K. So this is where cross entropy comes from. We are trying to maximize the fit of our probabilistic model to the data. Using maximum likelihood estimation. And with certain assumptions, we arrive at the cross entropy loss function. Okay, this was actually last week's topic, but this was left over. If you have any questions, we can talk about it. The same thing written in other form, yes. Here? This one. Because each element in a yi vector is either 0 or 1. Right? Here, it's a one-hot label. If I don't put this exponent, what will happen? This product will just be 0 because we know that at least one of them is 0. But if I put this exponent here, the 0 terms will convert to 1. And the term that is 1 will stay 1. Okay. So that's the reason. K in the softmax here, this one, because I want to take a sum over classes, and I don't want to use C because it's used here. It is used here. That's why I want to use another variable. That's why I chose K. Okay, so let's start today's topics. So we will start with artificial neuron, and we briefly looked at it and made analogy to the biological neuron, where these weights take inputs from other neurons, and this is similar to the input time weights are summed together. We call this the net input. It goes through an activation function. If it's high enough, the neuron outputs something, otherwise it doesn't output anything or output 0. The history of this artificial neuron dates back to 1940s. The first artificial neuron model was McCulloch-Pitts neuron. It was also called the linear threshold logic unit. And the whole purpose of this Markov-Fitts neuron is to compute Boolean functions. So there is no learning here, no training. All they want to do is to represent these Boolean functions, which are, you know, and or not, and there are others, by artificial neurons. So, for example, if you want to implement an AND function, what you do is you take the input x and y, multiply them by +1. You add a bias term, a constant term 1, and you multiply it with -2. And if you do the math here, just multiply the input with the weights, sum them together, and then apply this threshold, which is if the net input is positive, it will output something. If the net input is negative, it will not output. It will output 0. And you will see that this implements the AND function. Similarly, you can check OR and NOT. NOT is very easy. You take the negative, so multiply it with -1. If it's positive, you output 1. Otherwise, you output 0. So this, if x is 0, then this will output 0. But I guess they represent binary by -1 and +1, probably, because this does not work otherwise. But anyway, this is just the historical knowledge. We don't use these things today, but just to show you that this neuron modeling started in 40s, and perceptron, which we use in neural networks in today, every day, was proposed in 1958 in the journal Psychological Review. So it was actually a psychology, that journal still exists today. It's a very reputable journal. It takes real valued input as opposed to the previous one, which took binary inputs. And this can do two-class classification. So you no longer restricted to Boolean functions. This now can do classification. What it does is takes the input vector x, multiplies it with the weight vector, and if that dot product is positive, then this outputs 1, otherwise it outputs 0. Interestingly, to learn, so this is trainable, and interestingly, Frank Rosenblatt proposed this learning rule to learn a perceptron. Can you see why this works? So this learning rule, look at it. So you take the current weight vector and add to it the ground truth label minus the prediction of the perceptron. So this is like a prediction gap times input and with a learning rate. So this is not gradient design. This is not a gradient, right? This is something else. That's why we call this the perceptron learning rule. And it works. Can you see why it works? Yeah. Yes. Yes, the proof is actually based on that. So let's multiply each side by xi transpose. So I will multiply, let's see. Xi transpose W next is equal to Xi transpose W current plus eta learning rate yi hat xi transpose xi. So what we notice here is this term is quadratic. So it's a square of something. It's a square of x. That's why it's always positive. Because it's always positive, now we can reason about whether W next is larger than W current or the other way around, right? So first of all, if the prediction is correct, that means if yi equals yi hat, then there is no, the learning rule does not update anything because this is 0. It updates the model only if there's a difference between the label and the prediction. And if, let's say, for this example, our label is 1, and the model predicts yi hat as 0. Now we have a wrong prediction, and according to this rule, this part will be 1. So this part will be positive, right? That means xi transpose w next will be larger than, it is guaranteed to be larger than xi transpose w current. Do you see that? Because on the right-hand side, we have a positive quantity. So for this condition, we know that this inequality holds. That, and look at the classification model, which is again a dot product. So you are actually, for a positive example, you are actually increasing this dot product by this learning rule. That's why it works. And if you inspect the other way around, if the correct label is 0, but the model predicts 1, this inequality will be the other way around, and that this update rule will guarantee to decrease the dot product. Okay? So in learning, we are not actually restricted to gradient descent or backpropagation. This is just one learning rule that you can prove to work. And actually, there is some recent research where you try to use non-differentiable functions or computational blocks within neural networks. And so you have a non-differentiable block, but you have other differentiable blocks. And you want to use backpropagation, gradient descent, but you have a non-differentiable block here, which does not give you a gradient, but you get the pseudo gradient or an approximate thing using this perceptron learning rule. So it is still being used by current research. That's what I'm trying to say. So perceptron learning rule works, and here is a nicer proof, but it's the same thing. It shows both cases, when the label is 1 and when the label is 0. And correspondingly, the dot product is either increased or decreased. So that's why it works. So later, after perceptron in 1960, we have the ADA line, which stands for adaptive something. I forgot. Adaptive, I don't know, adaptive linear something maybe, by Widrow and Hoff. This is very similar to perceptron, but it has an improved learning rule, which is shown here. So what is the difference? Yes, it uses the function directly, but yeah. So in perceptron, we were using yi hat for this part, right? But yi hat is a result of a thresholding function, so it's binary, 0 or 1. But W current Xi is not binary, it's a continuous thing. So that's why it's an improvement to the perceptron learning rule. So in Ada line, the error here is proportional to yi minus the W current Xi, and that's why they said this is working better because the error is proportional to the error instead of this binary thing. And then, of course, there are other artificial neuron models, but most of them are trying to model the neurons in the nervous system neuromimetically. So they try to actually simulate the spikes and spike rates and so on. So they try to be as faithful biologically as possible. But those models are not really being used in modern deep neural networks. There is an active research which try to use those spiking neurons, but they never make to the top benchmarks or top results. So we still use as the artificial neuron model a simple thing as perceptron. Okay, but there are much more complicated, advanced neuron models that mimics, for example, a monkey neuron in the retina, retinal ganglion cell or lateral nucleus cell, very precisely. So we have those models actually, but they are not being used in modern neural networks because the goal there is to model the biological behavior as accurately as possible. But here, this is a simple mathematical model to solve a specific task. And therefore, we use this kind of perceptron-like neurons in modern neural networks. And then after 1960, the other important milestone is 1986, which is the backpropagation paper by Blumenhardt and Hinton and Williams. This is in 1986, and this was published in Nature, Learning Representations by Backpropagating Errors. And it's actually a way of computing the gradient of neural networks. For this paper is usually cited, but it was actually invented many times in history. And if you are curious, you can check the history section in Wikipedia page. It's actually, there are many times backpropagation was invented by others, different groups. But actually, it's an efficient application of chain rule in calculus, nothing else. In first week, remember we said that a neural network is a stack of linear and nonlinear operations. And to get the gradient of this composition, you just apply the calculus, chain rule in calculus, and that gives you the gradient, that's it. Backpropagation is actually the application of that. So to compute the gradient of the error in the output layer, one has to compute the gradient iteratively, layer by layer, from the output to the input layer. That's why it's called backpropagation. We are going to get back to its details later, but let's briefly talk about it here. If we consider this black box as our neural network, there are layers here. They are either linear operations or nonlinear operations, right? And then they do some computations. And at the end, you apply softmax here. Of course, you don't have to use softmax in every neural network, but we are talking about the supervised classification example again. That's why I put softmax there. And you usually have a ground truth label. You usually have a loss that computes the discrepancy between prediction and Y. And you want to actually, let's say there is this theta 1, the parameters of the first layer. And what you want to do is find the derivative of or the gradient of loss with respect to theta 1. This is what you want to find. Because if you find it, then you will update the parameters in the first computational block, first layer, by the negative of this gradient. And in order to do that, you need to start all the way from the loss. So the derivative of loss with respect to y hat, the respect to, let's say this is theta n. So we are going to look at this, but yeah, it's something like that. So it's the multiplication of derivatives of the input of the next block with respect to the output of the previous block, and so on. You stack these things up, and then overall they become the gradient. And this is what you use to update the model parameters. Okay, so now let's build MLPs. Now that we know a single artificial neuron, how it works, now we want to combine these things into a network and then create this network called multilayer perceptron. This is called multilayer because input and output layers are also considered as layers. And even if you use just one hidden layer, this is still called MLP, but you don't have to have just a single layer. You can have as many as you want here. And this is a fully connected feed-forward network. We are going to see different types of connections, sparse connections, parameter shared connections, right, in CNNs. But this is in this example, you see a four-dimensional vector as input. So you can think of this as X. It has 4 elements. There are 5 hidden nodes here, and each with a 4-dimensional weight vector. For example, if I consider this neuron, it has connections coming from the previous layer. So 4 connections, and each connection has a weight here, right? V1, V2, V3, V4. And each of these 5 neurons have such weights, and they are all different. It's better they are different. I mean, better. Otherwise, there will be redundancy. Okay. So remember from first week, Cybenko's universal approximation theorem. Multilayer perceptrons are universal function approximators. So you can approximate actually any function using MLPs. So they are that powerful, very powerful. And it was the most popular classification algorithm in 1980s until support vector machines and kernel trick were introduced because they had these convex loss functions, and MLPs have non-convex loss functions. They got stuck in local minima, and people started not using MLPs. But today we use them. Okay, back to our example now, little bit more math. Let's say, again, this is our input. It's a 4-dimensional vector, and let's consider this specific neuron, and its weights are represented by W5, again a vector, because it has connections from here, 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 and there. And what it does is, as a computation, it does this, takes the dot product W5 times X, and then passes through the nonlinear activation. And this determines the output here. And then in the next layer, in the output layer, a similar thing is happening. That output neuron also has weights, theta in this example. So it has 5 weights, these ones. It multiplies its inputs with those weights and takes the sum, and then no nonlinearity is shown here, but usually you do something with this output, right? You compute a loss, and that loss function has some nonlinearities. For example, if you use softmax normalization, it introduces these nonlinearities here. Actually, that's it. MLPs are. Which one? Omega 5 is 4-dimensional, yes, because it has 4 inputs. Where? Okay, at the output layer, you can or you choose not to. Both are fine, but usually applied, because if you want to take the, so let's say this is y hat, and if you want to compute a loss between this one, and usually you apply softmax to this before passing it to cross entropy. And softmax is not called an activation function, but it's a nonlinearity. Yeah. So we'll talk about activation functions next, but I want to ask you a question at this point. So simple models like perceptron or ADA line cannot solve the XOR problem, which is this. Why? Because we talked about this, right? Perceptron implements a linear decision boundary, ADA line also, and you cannot separate positives from negatives using just a single line. But MLPs can solve it, can solve the XOR problem. And I'd like to ask why. Is it because of having many neurons in the hidden layers, or is it because of the activation functions used? What do you think? Yes.
Because the activation functions every month with everything.
Okay. Any others? Huh?
Because it has many neurons, but not including non-linearity.
Yes.
Because of like combined functions,
Yes.
linearity will be taken.
Yeah, very good.
It could be about number of multiple neurons. We cannot separate it with a single line, but we can separate it with the 2 lines. So maybe the number of other perceptron may have only 2 lines or separation.
Okay. Any other thoughts? So it's actually, the answer is actually the activation functions used. Because if you don't use any activation function, you might have however many neurons as you want. It will still be a linear model. Okay, it will just be a giant linear model with many parameters, but it will be a linear model, and this linear model will implement a linear decision boundary. It cannot do 2 lines. It can do just 1 line. That's why activation functions, the nonlinearities between the linear operations, is the critical factor here. Otherwise, you cannot solve this problem. And I'd like you to check this online demo. Let's go over it quickly here. playground, TensorFlow, playground, TensorFlow. Yes. So two hidden layers without activation in between. What do you think? It can solve it. Um, but there's no nonlinearity anywhere in the network. I give this as a homework assignment to you. My answer is no, it won't solve it because it's a linear model. You need nonlinearities. And maybe this demo will convince you, okay? But yes, first. Yes. Yes, your friend is saying, why not use feature engineering at the input layer? But that's, yes, that will work, but that's also introducing nonlinearities to the model. It's a way of. And here, actually, there is also squares, square x, x time x, and so on. So in this TensorFlow, I need to share the screen because otherwise okay, I'll find it later. Then okay, this is such a nice playground where you can choose a task. For example, it's on the top left called as data. You can, by default, it's the circular data set with a ring outside, but you can also choose this XOR problem, or you can choose a simple linearly separable data, or again, another very challenging data set, spiral data set. And the task is to find a decision boundary to discriminate these two classes. And you can play with MLPs here, actually. You can increase the number of neurons in the hidden layer or decrease. You can even add another hidden layer. But let's start with 3 neurons in the hidden layer. At the output, we have 2 neurons. Each will is computing with the, a class. And if you hit the play button on top left, it applies back propagation, gradient descent, and finds this decision boundary for you. So as you can see, the decision boundary has a triangle-like shape. And it's because of the 3 neurons that we use in the hidden layer. If I increase that to 6, for example, and hit play again, you will get a smoother boundaries, not a triangle, but now it's like a hexagon or pentagon, I don't know. If we introduce another hidden layer and hit play again, Now this becomes more smoother, the boundaries. You can choose learning rate on top. You can choose the activation function if you choose ReLU, for example. So let me show you the ReLU with the 3 neurons again. It couldn't solve it. Okay, this is what I wanted to show. ReLU, because it has this flat and then linear activation, you get this corner-like boundaries. Previously, it was tanh, it's smoother, and with 4 neurons, with just one hidden layer, it couldn't solve the problem, as you can see. If I add 2 neurons more, yes, it will do it with this, again, linear, but piecewise linear boundaries. So yes, play with this and try to get an intuition. You can play with the other more challenging data sets. Spiral, I think, is the most challenging because it has very fine-grained boundaries. As you can see, it couldn't solve this problem. Here you see the train and test losses on top right. There is also regression as well, but yeah. Okay, let's take a 10-minute break and then we'll finish. Okay. I was muted all the time. The alternative to training from scratch is grabbing a model, already trained model off the shelf from Hugging Face or somewhere else, and then starting from that. It's also a kind of initialization, right? But if you want to start from scratch, you should be careful about how to initialize the weights, because if you are not careful, then you would get your gradients, you will have numerical stability problems. So let's talk about that. Starting with all zeros might sound like a good idea, but it's not. All zero initialization. Can you see why it's not a good idea? Yes.
Always with zero, then all the inputs of two neurons are zero, then gradients will be the same, so the updates will be the same.
Yes. So suppose you have two neurons in your hidden unit and they have all zero weights, then they will compute the same output, and that output's influence on the cost will be the same. So these neurons will receive the same gradient, and they will update with the same gradient, so they will be identical neurons. So there will be redundancy. In fact, this happens with any constant initialization, not only with zeros. If you initialize with constant, it's a problem. Therefore, we initialize with random values, okay, not zeros. So to break the symmetry, so we initialize it with small random numbers. For example, you sample from the normal distribution, zero mean unit variance. If you multiply this with the value you want, this now reduces the variance of this, right? It's still zero-centered, but the variance will be much smaller because of this multiplication. This is good because it breaks the symmetry. Now, the gradients will be different for different neurons, which is good. But this could lead to two different problems. So let's talk about that. The two problems are, first, gradients might vanish due to very small numbers. If you get very small numbers, you keep multiplying very small numbers, you will approach zero. And this will vanish your gradients. And the output from a randomly initialized neuron has a variance that grows with the number of inputs. This could lead to very large responses. So this could lead to the exploding gradients. I will talk about this in detail in the next slide. So consider this perceptron with weights W and input X. What is the variance of this dot product? Of course, to answer this question, you need to assume some distributions about W and X, right? Let's do that. Assume that elements of W are independent normal random variables and X is a constant vector, which is reasonable because this is coming from a data set, and you can assume that W are sampled from independent normal random variables. Then W transpose X is a sum of normal random variables, each scaled with a positive or negative number coming from the elements of X. Now, the variance of sum of normal random variables, if you remember from your statistics classes, we are trying to find the variance of this here. Remember, if you scale a random variable with alpha, you get this alpha square variance of the original random variable. If you sum them or subtract them, you also sum their variances. So based on these facts, with more dimensions, so the larger your weight vector, the larger the variance. So the variance increases with the number of weights your perceptron has. Okay, so this is very important. I'm not going to do the proof of this why variance increases. It's here in the slides. You can check if you want. Basically, in the perceptron, if you have more weights, the variance of the output will increase. If you sample the weights from independent normal variables. And this is a problem. So as your weight vector is increased, you get more parameters, the variance is higher. And this, if you don't control this properly, then you will get exploding, you might get very large values. And since you multiply them, you get exploding gradients. These might sound very intuitive or simple or stupid to you, but these are actually the reasons, one of the reasons why neural networks did not work very well in the 1980s. Okay, so these are actually very important because people initialized them without being careful of this variance. They got this exponential or vanishing gradient problem, and it didn't find good solutions. But now, fortunately, we know how to do this properly. The solution is you calibrate the variance by, instead of sampling your weights from just this, you sample it from here. So you add a factor which accounts for the number of inputs or the number of weights to the layer. Okay, as the number of weights increase, this n increase, what you need to do is to sample from smaller and smaller values. The variance of the Gaussian should be smaller. Otherwise, you will get a increasing variance. But when you do this, it is controlled. You will always get the same variance, regardless of n. This is called Javier initialization, and it is already implemented in your favorite deep learning package library. This is implemented in PyTorch, in TensorFlow, in maybe others. But usually today we use the Kaiming-He initialization. This was proposed in 2015, and it's very similar to the Javier initialization with a corrective factor. There's only this 2. So as I said, you don't need to do anything today. When you create an MLP and initialize it from scratch, it does this. Okay, you don't have to do this explicitly. The library does it for you. But yeah, this was a very important, actually, discovery. Yes. I believe so, yes. Because each of them, whether it's a CNN neuron or MLP neuron, it has a number of inputs, it has a number of weights. You should control the variance when you initialize the weights. Okay, so we don't need to do anything. The libraries do it for us. Similar to backpropagation, we don't do it by hand, but we should know what's being done in the behind the scenes. Okay, we should be aware of what's being done. All right, let's talk about backpropagation and basic algorithms to optimize multilayer perceptrons. So we want to solve this loss function parameterized by model parameters theta. We want to actually find its the best parameter values that minimizes this loss. And to do that, I'm going to actually arrive at gradient descent, but I'm trying to explain where it comes from. Okay, why do we use gradient descent? So it is a modeling based on Taylor expansion. If you expand the loss function around a parameter theta 0 using the Taylor expansion, you get this expression, right? It's the constant L of theta 0, and then the first order term, the second order term, and so Now, similar to what we did with the perceptron learning rule, so let me work in this blank page. So we expand fx around a, let's say, let's be precise, x equal to a. Now, fx is approximated by fa plus f derivative a xa. This is Taylor expansion. So f x minus a squared plus the higher order terms. Now, let's ignore the higher order terms. Okay, we want to do a first order approximation. Now, all we have is fa plus derivative of f at a times x minus a. So let's evaluate this approximation at x is equal to a plus a small step, a delta x. Let's call this a small step. So when we evaluate function f at this new location, so I'm going to use the Taylor approximation here. We still get fa plus f derivative. Now x minus a will become a plus delta x minus a. So these will cancel. We are going to have fa plus delta x. Okay. Now I can choose. Let's choose this small step, whatever I want. I am choosing it minus eta times f derivative a. Then what we have is, so f naught plus delta x is equal to fa minus squared. Yes. And then from here, because squared is always positive, again, we have a quadratic term. So I know that fa is larger than always fa plus delta x. So this is the basis for gradient descent. If you choose your delta x as this form, minus learning rate, the derivative at a, then you will have this inequality. So this is the basis for gradient descent, why we are doing gradient descent. But of course, the intuitive explanation is without doing all these derivations. The gradient gives you the direction where the function has the steepest increase. And if you take the negative direction of it, now in this direction, the function will decrease with the steepest decrease. Okay. Yes. Okay. So in the numerical optimization literature, there are first order methods like gradient descent, steepest descent. There are, and also second order methods where the Hessian is involved. The second derivatives are involved. The second order methods are good because they give us also some guidance on choosing the step size, the learning rate. But because the Hessian is involved, and because we are working with billion parameters, million parameter models, computing Hessian and maintaining it is no option, is not an option. Therefore, although these nice methods are there in numerical optimization, today we are not using these methods in deep learning research. Instead, we use the more scalable and simpler methods based on stochastic gradient descent, which is a first order method. So we are actually trying to do with a simpler machinery. We know that there is a better machinery out there, but it's very costly. But as the GPU memories are increasing day by day, maybe for small models, we can use now these second order methods. I'm sure people are working on this, but I cannot cite any research on top of my head. But this is a research topic in itself. Okay, so famous stochastic gradient descent algorithm, which we use all the time to learn a deep neural network. We require a learning rate, which is shown as epsilon k here. We require an initial parameter theta. Remember, we initialize this using the hair initialization method by controlling the variance. And this is, as we will talk about the learning rate, mostly by trial and error. So once we have these things, we repeat this loop until convergence. We should have a stopping criterion until that is met. We sample a mini batch of M examples from the training set. M is the batch size here. We grab their corresponding targets, compute the gradient over these M examples. Now this is the stochastic gradient. And we update our parameters by minus times learning rate times the gradient. This is stochastic gradient descent. Very simple to implement, and it works in practice. But how is it done? I mean, how do you find this part is the question for backpropagation. And let's do this backpropagation by hand example, and then we can take a break. So given this artificial neuron, which is a perceptron actually, we want to compute this partial derivative, the derivative of loss with respect to W3. So a specific weight term. And this is for just as an example. You can compute the derivative for other weights as well. Here, as you notice, on the left-hand side, we don't have the function L. So the loss is not given explicitly here. So I don't know what loss is, but I can say that loss will depend on the output of the neuron O, right? So I can write that. And the output will depend on the net input of the neuron. And then the net will depend on W3. This is the chain rule. And let's look at each of them. This one, we don't know because there is not enough information given here. If the problem gives us the form of L, we can, the function which relates O to L, then we can take its derivative, but here we don't know. What about this one? Derivative of O, the output, with respect to the net input.
Zero if it's on the threshold, and otherwise it's the derivative. It's a slope of the threshold.
Yes, so, but it depends on the activation that is used, right? Depends on phi function. And for example, if phi is sigmoid, let's say, then this derivative is equal to sigmoid times 1 minus sigmoid, as we have seen in the previous slide. But if it's a step function, that's a lost case because all derivatives are zeros there. So we usually don't use that. What about the last term? X3, right? That's it. This is back propagation by hand. Of course, this is a very simple example. Let's do a more complicated example after taking a 15-minute break. Okay. Okay. Hi again. Let's continue. So I'm going to do another back propagation example, which I prepared before. So consider this network which takes x and as a neuron. So let's represent this neuron with weights W sub A, and this outputs, let's say, O1, and this is further fed into another neuron, WB, and there are other O2, O3, O4 inputs. And then this time I will also give the loss function. And let's say we are doing a regression loss this time, not cross entropy or hinge loss or any other classification. T represents the desired output. And then both WA and WB use sigmoid as activation. So this is the problem, and we are asking the partial derivative of loss with respect to, again, W3, but this time WA3. So the third weight of this first neuron. So what is this derivative? So it's very simple. We apply the chain rule. We start with partial loss WA3 is equal to W partial loss with respect to what? We start with Y because it's the output of the network, right? And then W partial of Y with respect to net B, net input of the second neuron, derivative of net B with respect to O1, because it affects the first neuron. Derivative with respect to O2, O3, O4 are irrelevant here. Partial of O1 with respect to net A with respect to A3, and this concludes the chain. Okay, now let's try to take the derivative of each term. So the first term, what is this? Y minus t, right? The second one here, output of the second neuron with respect to its net input. This is actually the derivative of the activation function. And we said that we are using sigmoids. Assume that we are using sigmoids. So this is the derivative. What about the next term? Wait. A. B1. Weight B1. You see? So because it's the derivative of net input of B with respect to O1, so we are talking about this part. Okay. And this is again the sigmoid. And the last term, X3. Actually, this is it. This is doing backpropagation by hand, but fortunately, you don't do it every time. PyTorch does this for you with its auto differentiation feature. Yes. Okay. So net B is the summation of O1, O2, O3, O4. So the derivative of this summation with respect to O1 is, sorry. The net B is the summation of O1 times WB1 plus O2 times WB2 plus O3 times derivative is the way. Now let's write it because there's a question about, so this one, net B is the sum of O1 WB1 plus O2 WB2 plus O3 WB3 plus O4 WB4. And the derivative of this with respect to O1 is the weight itself here. Okay, any questions about this?
Weight depends on B1. In each order, we update the weights. It's like a update weight from the last layer to the first layer, or they update at the same time.
You update them at the same time, but their vectors are all different. So here we calculated the gradient for WA3. So this is the update for WA3. You calculate the update for WB1 separately, and then update everything at the same time. But because of this chain rule, there is a lot of computation is common. So, for example, when you want to find the gradient with respect to WA2, most of the terms here will be the same. So that means when implementing this, you should be careful. You should be caching all these values in the backward pass so that you reuse them for, because for calculating the gradient with respect to these weights, all the gradients here will be reused. They are the same. But at this last step, because of this multiplication, each weight will be different, will have a different update.
We will have a different gradient if we update B1 first.
No, you don't update B1 first. You update everything at the same time. So let's say you freeze this network as it is right now. Calculate all gradients like this chain rule for every weight in the network, and then update everything.
What is change mean result for the direction we go?
Why would we update sequentially? I don't see the benefit of it.
It's about the benefits,
Mhm.
but it's like increase it, if the result is changing while we update the first stage, but at the end, the place will change or not.
So if we calculate the gradient per weight and then update them at the same time,
That's approach one. Another approach is updating from the latest to the first layers.
yes, but I'm asking why are you doing it? You can also do it from the other way around, right? So which direction? No, approach one is correct. The other approaches are, I don't know, because in gradient descent, what you do is calculate the gradient of loss with respect to all parameters. All parameters in the network. This is a huge vector, giant vector. And you update everything at once. What you are suggesting is, let's update some of the elements of this vector before others. Why? Why are we doing it? I don't see a benefit for that. Okay, think about it, and if there is still a question, we can talk later.
So always we the birth of the given weight, calculate the gradient times all those we want use them for the gradient.
I didn't understand the question. Can you?
I mean, we always use the all one first half of given there when calculating when you the back calculation. We don't use all two, all three, all four.
So we are using O1 because the first neuron is connected to the second neuron through O1. If it was connected through O4, then we would use O4. So it's just the architecture. So I can take this connection and connect it through O4. Then the chain will change here. So this would be O4. This will be O4. So this chain is based on the given architecture.
So very basic scale, but the loss actually is the gradient loss is consisting of I don't know how many weights and the basic corresponding vectors. So what I'm saying is a single scale scales
Everything.
everything.
Mhm.
So
Yes.
how does this make
Yes. So the question is, we calculated the gradient with respect to all parameters. So I'm butchering the terms here. Gradient is the vector of all partial derivatives of the model. Okay, so this is the gradient vector. And your friend is asking, we are multiplying this with a learning rate, eta, let's say, and taking its minus and updating the theta with this. He's asking why or how a single scalar eta works for all of these many parameters. In some cases, we have billions of parameters. How does it work, right? So there are actually per parameter adaptive learning rate methods. ADAM is such a method. ADAM is actually updating its learning rate per parameter. So it is actually addressed by those methods. But in plain SGD, it's like this. There is no per parameter update. It's just eta scales all elements of the gradient at the same amount. Yes.
Or
Per input.
Or also in
Not per input, but per batch. So you take a mini batch. That's why it's stochastic gradient. So you randomly sample n examples. You calculate the gradient over those, not the entire data set, and then update the model with this gradient.
Maybe I ask it from at least updating
Hmm.
for class feature per feature.
Per element of the gradient.
Not the hyper. This is like the eyes.
Not the hyperparameters, no. The learnable parameters only. Everything clear? Any other? So stochastic gradient descent. So let's talk about how should we set the learning rate. That's very important. And unfortunately, this is more art than science. We are choosing it actually by trial and error. We can use methods such as grid search or Bayesian search, but this is still not science, it's an art. But of course, we know some things, and these are very little, but here they are. If you use a constant learning rate, and if it's low enough, then you are guaranteed to make a zero or positive progress. In the break, one of your friends were asking me, why are we why do we need a learning rate? The answer is, if your loss function, let's say, is quadratic like this, and you are here, your current parameters are here, if you take the derivative will give you this direction because it's the direction where the function increases, and you take the other direction, negative, so you need to move this direction, but you don't know how much. If you take a very large step, you might even end up here, which increases the loss. We want to decrease the loss. So that's why taking small steps is usually better than taking very large steps. And when it's low enough, you are guaranteed to make zero or positive progress. So take a small step, you will be here, you will be there. So you will take small steps and improve. Another thing is you decay the learning rate usually, because learning rate is decreased as a function of the iteration number. Decaying is desired because the gradient estimate is noisy due to the random sampling of M training examples. This introduces a noise. And this noise does not vanish even when we arrive at a local minimum. That's why you reduce your learning rate, and this subsequently reduces the magnitude of noise in your training. By decreasing the rate, the source of noise is progressively eliminated, and there are LR scheduling methods You might have heard of step decay, exponential decay, linear decay, or cosine annealing. These are all methods to modify your learning rate given the iteration number. They usually decrease it, but things like cosine annealing, there are warm restarts. So in cosine annealing, learning rate is increased and then decreased, increased and then decreased. So this is active research of area of research actually. Practical tips. You should always plot your training loss curve. No question, no exception. You cannot say, oh, I'm looking at the log, text log, and I'm looking at the numbers, they are decreasing. This is very, you cannot rely on that. You cannot rely on your judging the numbers by eye. You should always plot the curve, and you might get different types. For example, if you get a curve like this, the first one, what can you say about your learning rate? It's very high. Because usually this is a minimization and your loss should go down, right? But if it's going up, that means your learning rate is very high. So you should reduce your learning rate. What about the blue curve, the 2? It's not optimal, it's slowly decreasing. Maybe learning rate is small here, too small. You need to increase it. What about 3? The green one? What do you think? It's tricky, right? It's not, it's like art. So 3 is actually, there is a sharp decrease at the beginning, which is good. But then it stays at a high point. By high, I mean, so you should check the loss value that it converts to, and you should assess that value. Is it good enough for your task? For example, if you are using, let's say, a regression loss in a regression task, and it converts to some certain value, which is here, think about that loss. Is it, on average, good value for your task or not? If it's not, then this means that, again, the learning rate is high because it quickly decreased and it converts at a very high loss value. This is a signal that you should decrease your learning rate. And for the red curve, among these 4 things is the ideal one. You get a exponentially looking decrease at the beginning, and then it converges to a low loss value. This is ideal. But again, how low is low is something that you interpret given your task and loss function. If it's cross entropy, you should think on, for example, your loss is giving less than 1 cross entropy. It's usually good. But given your class, number of classes, you should do some calculations on paper actually, whether this loss value is good or not. But always plot your training loss. So these are the diagnoses here. You adjust the learning rate and learning rate scheduler to get a good curve, something like the red curve. And by adjust, we mean search. Grid search, Bayesian search, and so on.
Does short can also mean that we start in local minimum?
Which one?
Third one.
The green one.
Yeah.
Yes, definitely. Yes.
So we didn't do warm up or start with a high learning, right?
Yes.
So it converts what? High.
Yes, it converts in a local minima, we can say that. And yes, we can try different random starts, but also we can try to increase the capacity of the model. Contrary to the intuition coming from statistical learning, you can increase, and the double descent phenomena says that you will get a better local minima with a larger model. Okay, so, and you also evaluate the converged loss value. Is it good enough or not? You should, this is an interpretation task. There is really no, you should, yeah. So for just a second. For this to be interpretable, you should design your loss to be, for example, per example. Loss per example. So if you define your loss to be a summation over the whole data set, then it becomes not interpretable. But if you define your loss as a cross entropy y like this, then what you get here will be per example average loss. Then that is something interpretable, one single example. But if you don't use that n here, then you get a less interpretable loss value. Okay. So these are some practical tips that you consider. The last topic is momentum, but there are some derivations here. Maybe we can stop the topics of this week at this point, and then I can give you the quiz. But before that, any questions up to, yes? Okay, what would the curve look like if we first reach a local minimum and then global minimum? It's very difficult to answer this question because in over-parameterized deep neural networks, there are many local minima as good as global minima. So maybe in the red curve, maybe that is happening. You don't know. Okay. But with classical statistical learning, with small models, what you are asking would look like this. So you start with a loss. Maybe this is the local minima, and then you reduce learning rate. The model escapes from the local minima, and then it can do like this. So from here. So this could happen. You reduce the learning rate at f of 10, for example. The loss might have a jump decrease. Okay. Yes. For if you are using cross entropy, how can you understand whether it's a good loss value, right? So depending on your number of classes, you just work it on pen and paper, okay? And you will get some value. Okay, that's the way. Arkadaşlar sessiz olabilir miyiz?
Learning rate scale. Can we say that rate growth the learning rate becomes high and then low learning rate, so that we get and the reason
for the green curve?
Yes.
Okay, the question is, the reason behind the green curve, could it be because of the learning rate scheduling? Yes, it could be, of course. And there is no better way than choosing a trial and error, by trial and error. You should also, so you should search for the optimal learning rate and also for the optimal learning rate schedule. You should try these things. Okay, let me give you the quiz then.
Adamın her bunu söyleriz.
Tamam, gelecek.
Onu bitti.
Kayıtlı olmayanlar.